last lecture I had a misprinting on the slip equation. So I just would like to remind you that I have written the equation with a small mistake. The slip is supposed to be equal to ns minus ni divided by ns. If it is a percentage, it should be multiplied by 100 in order to get the percentage slip. Which supposed
دكتور الصوت في وشة صاير.
صوت في وشه الحين
اي مو واضح يعني.
خليها الحين شلون؟
بعد نفس الشيء دكتور.
لأن أنا المرة الماضية تقريبا ضبطته بعد شوي كان هو لما يطلع صوت الفم من هالشكل صوت الفم
اوكي.
بس ما أدري إذا المرة الماضية أنا سويت شغلة واضح الصوت ولا لا؟
للحين دكتور.
بس أنا صوتكم واضح عندي فما أدري إذا أنزل الصوت يمكن تحل الوشة احتمال. شلون الحين تسمعوني؟
للحين في وشة دكتور بس نسمعك يعني.
تسمعوني الحين؟
دكتور احنا نسمعك بس في وشة صاير يعني داخل على صوتك نويز. الحين ما نسمعك دكتور. ما نسمع لحد الآن. بعد ما نسمعك للحين.
تسمعوني؟
الحين نسمعك. إيه.
زين، ببند الميكروفون الحين بشوف إذا، لأن في اثنين ميكروفون، واحد مال الهيدفون واحد مال الكمبيوتر، فببند واحد منهم بشوف.
أوكي.
تسمعوني؟
نسمعك دكتور.
الحين أوكي؟
الحين هون.
خف الصوت يعني، خف الوش
أي
كذا.
خف. إيه بس موجودة لحد الآن.
موجودة بس خفت؟
إيه صوتك يغطي شوية.
أوكي. المهم إن الصوت يكون واضح، على أساس بحاول أبدل الميكروفون نشوف إن شاء الله. نرجع لموضوعنا. في الدرس الماضي أنا كتبت المعادلة خطأ، يعني كتبت سلب يساوي NI ماينس NS مقسوم على NS، وهاي المعادلة خطأ. في الدرس الماضي كتبت هاي المعادلة، هذه المعادلة. فالمعادلة الصحيحة هي هذه، موجودة طبعا في النوت، يعني واحد من زملائكم خبرني قال لي المعادلة مكتوبة خطأ، قلت له صحيح، راح أعدلها المحاضرة الجاية. أنا الحين قاعد أنبهكم إن المعادلة كانت مكتوبة خطأ في المحاضرة السابقة. فالمعادلة الصحيحة اللي هي هذه، سلب عبارة عن NS synchronous speed، لأن في الحالة المعادلة الخطأ في الدرس الماضي راح تعطينا نيجاتيف سلب مقسوم على NS. فهذه المعادلة الصحيحة داخل البوكس اللي هنا في الصف الثاني. ممكن نكتبها بعد، ممكن نكتبها عبارة عن 1 minus NI مقسوم على NS. فاحنا بالنسبة للسنجل فيز اندكشن ماشين عندنا تو سلب في الحقيقة. عندنا S forward which tends to rotate the machine in the forward bias, because you have two torques. You have two torques. The single phase induction machine, actually, this is the configuration just to show a simple construction of the single phase induction machine. Main winding, we have a main winding, and we have main winding, and then single phase induction machine supposed to include only one winding, which is the main winding, this one here, main winding. And the rotor, which has also its own winding, which is not connected to anything. It's a closed short circuit. But with a single winding, the machine in the positive cycle, the machine, let's say, is supposed to rotate in the clockwise. So the machine is supposed to rotate. In the positive cycle, the machine will tend to rotate in the clockwise, let's say, or counterclockwise, it depends. Okay? And in the negative cycle, the machine will try to rotate clockwise. Okay? The two forces are very fast, and the resultant rotation will end up with 0. So in the positive cycle, the machine will try to rotate clockwise or counterclockwise, it depends. And in the negative cycle, the machine will try to rotate oppositely. And therefore, the resultant torque will be 0. So the machine, the single-phase induction machine, is not a self-starting machine. It's not a self-starting machine. Therefore, we need to include another winding, which is called auxiliary winding. Auxiliary winding. Okay. This is the winding which has to be included. The auxiliary winding. And normally the single-phase induction machine has, some of them, not all of them, has a centrifugal switch. A centrifugal switch. It has a centrifugal switch. Okay. So it has a main winding. So in order to make the machine self-starting, we need to add another winding, which is called auxiliary winding, to make the machine self-starting. Because in the three-phase induction motor, you have 3 windings with the 3-phase. So you have a winding connected to phase A, winding connected to phase B, and a winding connected to phase C. So it's the 3-phase induction machine is a self-starting machine. But the single-phase induction machine is supposed to have only the main winding. So with the single winding, main winding, the machine is not self-starting. By adding an auxiliary winding, the machine is made to be self-starting. So in order to have a higher starting torque, we will connect also a capacitor. You can say a starting capacitor, or a series capacitor added to the auxiliary winding to make it, to enable the machine to have a higher starting torque. So we can determine the value of this capacitor later on in this chapter. So normally, some of the machine have a centrifugal switch. This switch is normally closed. So when the machine, at the starting, this closes switch. When the machine reach, after starting, when the machine reach up to, let's say, 70–75% of final speed, this switch is a mechanical switch. It's called centrifugal switch. Centrifugal switch. Centrifugal switch. Okay. So this is a mechanical switch. when the machine reaches 75% of its final speed, this switch will open. 70 to 75%. This switch will open, and therefore this circuit, the whole of this circuit will be out. After, when the machine is at full speed or at above 70% of its final speed, this circuit is out because the switch will be open. Therefore, at the starting, you will have the auxiliary, maybe an added capacitor, will be closed or connected in parallel with the main winding of the single phase induction motor. But at standstill, this switch is closed, and therefore the auxiliary winding and the capacitor are connected. But as I said, why we need to we can say that we have two torques, as I said, because due to the main winding, we have a torque trying to rotate the machine in the forward bias, and a torque which tries to rotate the machine reverse bias. We call it here backward. So we have S forward, and S backward. Okay, the S forward is the normal slip, which is NS minus NR divided by NS. Okay, which is 1 NS divided by NS minus divided by NR divided by NS. Okay, so we can, from that, we can see that we can write it like this. NR divided by NS. We can make the subject NR divided by NS, which is equal to 1 minus S forward. This is S forward. 1 minus S forward. And S backward, we can say that it is NS minus NR, because the rotor is trying to rotate in the backward or in the reverse. So minus, because the slip is NS, minus NR, but in the backward slip, NS minus NR, because the rotor is trying to rotate in the backward. Okay, which is equal, in this case, 1 plus NR divided by NS. So if we substitute, if we say this is, that this is equation 1 and this is equation 2. If we substitute for NR here, equation 1 into equation 2 for NR over NS, then we will end up with 1 plus 1 minus S forward, which is S backward in this case, is equal to 2 minus S forward, because we don't want to deal with two slips. So we have S forward and S backward. So S forward, NR divided by NS, is equal to 1 plus S forward. We can substitute this equation into here. So if we substitute for NR divided by NS into 1 minus S forward, then we will end up S backward is equal to 2 minus S forward. So this is the idea that in the single phase induction machine you have two torques. One tends to rotate the machine in the forward direction. The other torque tries to rotate the machine in the reverse direction. And therefore we will end up with zero torque. So the machine will not rotate. By adding an auxiliary winding, the machine will rotate in one of the directions. So by adding the auxiliary winding, the machine will be made to be self-starting and it will rotate in one of the direction, either forward or backward. This is something relative. Okay. So by a capacitor here, it's just to add a higher starting point. The capacitor will give the motor a higher starting point. So if we go to probably the next page, which is maybe this idea, you can say, this idea is shown here in this. This is the machine, a single phase induction motor with a main winding only. This is the main winding, okay, and the flux, which is created by the rotation. But anyhow, this is the, I believe you have taken this, which is torque slip characteristic. Torque slip characteristic, this is the torque, this is the slip. Torque slip characteristic. You have taken this. So the machine is not a self-starting. So with only a main winding, this is the torque slip characteristic. So it is not a self-starting. At starting point, the slip is equal to 1, because at starting the slip is equal to 1 and R is equal to 0. So NS divided by NS is equal to 1 at the starting. So when we add an auxiliary winding, the machine is made to be self-starting. Okay, it will have a starting point. And this is of course for the generator mode or generation mode. So this is generator, negative slip, or slip is equal to 0. And sometimes it's not the one like this. Some box you will find it. And this is motor mode. Motor mode and generation mode. Okay, sometimes it's drawn like this. Sometimes it's drawn like this. So this is generation mode, and they put the axis, they put it like this here. The axis, they put it there. So sometimes it's drawn like this. So this is generation mode, this is motor mode. So anyhow, so in the generator, you can say it's negative, or it goes to double the slip. But for the generator, there is no slip actually. When you have out of synchronism, then you will have the machine will retard and stall at the end. But anyhow, this is not our topic. So the machine is, as I said, it's not a self-starting when there is only the main winding. But when you add an auxiliary winding with a capacitor, then you will have starting torque. If you add a higher capacitor value such that the two fluxes, when the two fluxes which tends to make the machine self-starting, if the two fluxes are perpendicular as it is shown, when the two fluxes are perpendicular due to the two windings, then you will have a higher starting torque actually. You will have a higher starting torque, like this. A higher starting torque. It depends on the selection of the value of the capacitor. And we will see that in the last example in this chapter. Because we have, as I told you, we have only 3 examples. So, talking about the equivalent circuit, single phase induction machine equivalent circuit. So as I said, S forward is equal to this equation. So from here, you can say NR divided by NS is equal to 1 minus S forward. And S backward is equal to NS minus NR, because the machine is trying to rotate in the reverse direction. So NS, which is equal to 1 plus NR divided by NS. So if we substitute this in there, then we will end up with S backward is equal to 1 plus 1 minus S forward, which equals to 2 minus S forward. So this is because we don't want to deal with 2 slips in the equivalent circuit of the single phase induction motor. We want to deal with 1 slip. Normally, in the 3-phase induction machine, equivalent circuit is something like this. Let me see. So I will take the equivalent circuit of the single phase, so of the 3-phase induction machine, but let's say which is something like this. Of course, we have the parallel combination. The parallel combination of RC JXN, and you have, of course, or let me, you have like this. So this is R2 dash over S and JXN. Do you hear me? Are you following up? Hello? Are you following up? Do you hear me?
ايه دكتور نسمعك.
Yes.
Okay. Because as if I'm talking alone and nobody is following up. Okay. So this is the equivalent circuit of the single-phase induction motor. Sorry, the 3-phase induction motor. This is the equivalent circuit. If you remember from machine 1. From machine 1, this is the 3-phase equivalent circuit. JX1. All right. Now, this is because you can have, maybe I don't know if you have taken the equivalent circuit a little bit different. Like the rotor equivalent is not like this. Sometimes they draw it like this. I don't know. They have given you this as well. R2 dash into 1 minus S divided by S. And this is R2 dash, and this is JX2 dash. Okay, so this is the stator. This is Z1. Stator impedance. Stator impedance. And this one here, this is Zm. This is magnetic coil impedance. And this is Z2 dash, this one here, Z2 dash. This is Z2 dash, this one is rotor impedance. Someone will say, I don't know if you have taken this equivalent circuit for the three-phase induction machine. This one is called dynamic resistance. This is the shaft, you can say, dynamic resistance. So this is dynamic resistance, which is the slip-dependent resistance, which is the shaft, the final output power, you will get it from the shaft, which is a slip-dependent. Slip-dependent because the speed of the shaft is a slip-dependent, but the variation of the speed is more or less little. Not the speed will change in the three-phase induction motor when you overload the machine. When you load the machine gradually, you will have a speed drop because the machine is loaded with a mechanical load. So when you load the machine gradually, mechanically, on the shaft, the speed of the machine will gradually drop, but it will not, according to this, let's say, to the torque slip characteristic, according to the torque slip characteristic, and you have taken this, suppose that you have taken this on machine 1, so the machine at starting, the slip is equal to 1. So the machine will start somewhere here, let's say. And then it will end at slip equals 0. Of course, the machine normally operates at full load torque. This is T full load, or even T no load. Okay? Because the machine will not reach to this point. When the machine reaches to this point, it means that the slip is equal to 0, so the speed of the shaft is equal to the speed of the rotating magnetic field, the synchronous speed. So the slip will be equal to 0. Normally the machine operates somewhere here at no load. At no load, the machine operates somewhere here. So the full load is somewhere here, which sometimes it is even less than the starting torque, or it might be higher than the starting torque. It depends on the machine type, the machine characteristic. Okay, so this is when the machine at starting, you supply V and I to the motor, it will start here, and then gradually the machine will speed up, and it will reach to its final speed, which is somewhere there, if it, at no load. With a load, it might be working here. When you increase the load, the motor will operate somewhere there. You start overloading the machine gradually. The maximum load that the machine can withstand, it's here, which is called Tmax. This is Tmax. The maximum torque that can be supplied by the machine to your load is at this point. So when you gradually increase the load, this is T full load, which is normal, safe operating condition of the motor. So you gradually increase the load, the speed will retard, because as you go along here, at this point, NR is equal to 0. Therefore, the slip NS minus NR, which is equal to 0, divided by NS, so the slip is equal to 1 at the starting. So here, NR is equal to NS. Okay, so that's why the slip at this point. But of course, the machine will not reach that point. So when you start gradually increasing the load, the speed will be decreased. The shaft speed will decrease, and S is constant. It has nothing to do with the load. Okay, it's the rotating magnetic field, the speed of the rotating magnetic poles, and NS is fixed. But when you gradually increase the load, the speed of the shaft will decrease, and when you overload, increase the load up to the maximum here. The machine, at this point, it will give you the maximum torque. When you also increase the load more than the maximum that the machine can deliver, the machine will retard and it will stall. It will stall, it will stop. Once the machine stops, if you don't disconnect the supply from the motor, the machine will burn. It will damage. You will end up with a damaged machine. So if you gradually increase, this is the normal full load torque here, but the machine might subject, if you have a variable load, mechanical load on the shaft, the machine will be subjected, if you have a variable load, the machine, if the load is increased gradually, the maximum torque that can be delivered by the motor to your load is this, the maximum torque here. Some of the old books, they call it TPO, pull-out torque. But now in a new box, you will see that this is written as Tmax, maximum torque. Pull out torque, TPO. Okay, so when the load has increased more than the maximum that the machine can deliver, maximum torque, then the machine will retard in speed and it will stall. It will stall. And once the machine stalls and stops, then you have to disconnect the source. If you don't disconnect the mains, the supply, then the machine will damage. So this is the equivalent circuit. So the resistance here, the dynamic resistance, is slip dependent. And in this resistance, you will get the mechanical output, if you remember. If you remember, P develop is equal to what? P develop is equal to 3 R2 dash. This is for the three-phase induction machine. Into R2 dash into 1 minus S, if you remember, divided by S. This is the developed power by the motor. And in order to find T develop, you can say PD, P develop, divided by omega, like this. So if you neglect T developed torque, there is a slight difference between the developed torque and the output torque, which is P rotational. So T output is equal, or you say, and I change this, we can say that P P out is equal to PD minus P rotation. And if you remember, still you remember the equation of the three-phase induction machine. I don't know if they have given you this equivalent circuit for the three-phase induction motor. Why I'm exposing you to the three-phase induction motor while you have finished in machine 1 to the three-phase induction motor. I just want to give you and compare to you the difference between the three-phase induction motor equivalent circuit and the single-phase induction motor equivalent circuit. I don't know, have you taken, I just want a quick answer, have you taken this equivalent circuit, or was it the first one I have drawn in the single phase, sorry, the three-phase induction motor equivalent circuit? Maybe you have taken this equivalent circuit, the first one I have drawn at the beginning. Which is this. You can draw it like this. So this is JX2 dash, and this is I2 dash divided by S. This is IC, this is JXN. نعم؟ خذيتوا الاثنين؟ Good. So you have taken this one and you have taken this one, which is the same circuit. Because when you add this with this one here, with this, then you will end up, when you add, this is divided into two, R2 dash constant and a dynamic. You have a constant R2 dash, rotor resistance, and a dynamic resistance, which is slip dependent. So when you add these two elements, then you will end up with this element, which is the rotor resistance slip dependent. But they divided into two, a constant one with a constant power drop, okay, or power loss, and the useful power developed across the dynamic resistance, which is R2 dash into 1 minus S divided by S. This is the dynamic resistance, which is slip dependent, in which you will get the output power, the developed power. So this is the equivalent of the three-phase induction motor. Okay, but this is per phase equivalent circuit. The single-phase induction motor, it is something like this. Just to show you, it's something like this. Okay, so the single-phase induction motor, we will neglect this resistance because it is big enough, so we will consider only JXN. So they divide this equivalent circuit into two halves. So neglecting this resistance, we will have something like this. Why we neglected, I will tell you if we have time. So dividing this equivalent circuit into two halves. One trying to rotate the machine in the forward bias, and one is trying to rotate the machine in the backward, direction. So this is the single phase equivalent circuit. So this is Z1, which is R1 plus JX1, and this is R2 dash divided by S41, and this is, sorry, I should mention that it is divided into two, so it is 0.5, half the resistance, half of this resistance, which is 0.5 R2 dash divided by S41, and 0.5 JX2 dash, and this is the same, 0.5 JX2 dash, and this is 0.5 JXN. This is 0.5 JXN as well. And here we have 0.5 R2 dash divided by S backward. So this is S forward. So this is, we call it Z forward. And this one here, we call it Z backward. And of course, this one there is Z1. So this is the equivalent circuit of the single phase induction machine. This is the equivalent circuit of the single. So you have an impedance which tends to rotate the machine forward, which is ZF, and an impedance which tends to rotate the machine backward. So we have a slip 0.5 because we have divided. This is the equivalent circuit of the three-phase induction motor, which is JXM in parallel with this, R2 dash divided by S and JX2 dash. So we have divided the rotor into two impedances. The rotor is divided into two impedances. One is trying to rotate the machine forward, ZF, forward impedance, and the other impedance which tries to rotate the machine backward. Of course, at the resultant will be equal to 0, but at the end, by adding the auxiliary winding, the machine will rotate in one of either directions. But we don't want to deal with two slips. And we have proven previously, that S backward is equal to 2 minus S forward. So we will remove S backward here, and we will instead of S backward, SB, we will put divided by 2 minus S forward. In that case, both of them are S forward. So we substituted for S backward by the equivalence, which is equal to 2 minus S forward. 2 minus S forward. Okay? But I don't want to use forward then. Then, yes, tell me. Time is about to finish. Tell me. نعم. Yes, we always neglect RC. There is a reason. If you have, I said I will explain it to you. If you have two parallel resistance, one is, let's say, 10 ohm, and one is, let's say, almost 10 kilo ohm. One is 10 ohm, one is 10 kilo ohm. So what is the combination is equal to? Almost. Or if you wish more simply, we will say one is 1 ohm, the other one is 1000 ohm, 1 kilo ohm. So what is the resultant in the parallel combination? This parallel combination, what is the resultant? If you have two parallel resistance, one is 1 ohm, the other one is 1 kilo ohm. Exactly, it's almost 1. So the resultant is almost 0.1. So it's almost 1, 0.99. Okay, the resultant is 0.99, which is almost 1. So we can neglect the 1K. We can say we have that this is the same story. So RC is much bigger than JXM. So we can neglect RC and take JXM. So this is an approximation. Of course, it's not true. RC is there. RC is there. For the three-phase, we normally consider this. And for the single phase, it's there. But it's neglected for simplicity and fast solution. RC does exist. Okay? But we neglected on the basis of this fact. That two parallel resistance, one is 1 ohm, the other one is 1 kilo ohm. So the resultant is almost 0.99, which is almost 1. So we can neglect the 1K. Okay, so this is the equivalent circuit of the single phase induction machine. And since, because here, as I said, this is equal to SB. So I substituted for SB, which is 2 minus S for SF. In this case, we don't need to write SF because we remove SB and S forward. We can remove the S forward. And as I said, it's something relative. Suppose that the machine, this is, let's say, this is the rotor. So this is the shaft of the rotor. From one direction, if it is rotating clockwise, in the other direction, it looks that the machine is rotating counterclockwise. If you have a pen, and from your point of view to your pen, if you are rotating the pen, let's say any shaft, any stick, if you rotate the pen clockwise here, if someone is viewing the rotation of this shaft, if the shaft is rotating clockwise from one end, in the other end, it looks that it is rotating counterclockwise. So it's something relative. So the machine equivalent circuit will always be like this. Either the machine is rotating from the load side forward, or on the other side, it's rotating backward. Okay, counterclockwise. So if you are rotating the machine from your eye viewpoint, it will look clockwise. On the other side of the shaft, it's rotating to this person standing on the opposite direction, or on the opposite side of the shaft. It's rotating counterclockwise. So the equivalent circuit will always look like this. I believe the time is almost over, and I have to stop the conversation, the lecture up to here, and you can see the equivalent circuit. You can see the equivalent circuit, which is here. This is single phase induction machine equivalent circuit. Okay. Equivalent circuit. That's it. So you have seen the equivalent circuit, which is in there, and I will stop the conversation and see you by Tuesday. All right. Is there anything? I will stop the recording. And maybe